Good day everybody. In this tutorial I'm going to explain how we can use software called Swedge. So I'm not sure why it's called Swedge. So this is about wedge failure. So wedge failure, it's actually very common in rock mass. So this is what wedge failure looks like. So we have a wedge that formed in the rock mass, and then at some point, because of the gravity, it will just slide downward. So you see what we need to know here, these two planes. So this is the first plane and the second plane. So when we have these two major planes, you will see where they intersect each other. So this line is called line of intersection, and we will need to know some information about deep and deep direction of this line of intersection. In particular, we'd like to know deep, which is inclination. But if you watch my other videos, you will know that for a line of intersection of two planes, we don't use deep and deep direction. Instead, we use trend and plunge. So trend has similar concept as deep direction, and plunge has similar concept to the deep, but we just don't use it deep in deep direction for the line of intersection. So that's why we use trend and plunge. Okay, so what we'll need to know that probably plunge, and the good thing about this software is going to calculate trend and plunge of this line of intersection. The only thing that we'll need to provide it's a deep in deep direction of these two major planes, the one that will form this wedge that will go down at some point, right? This is pretty cool. You can just play with it, look around. This one, it's a view from the. Okay, this one doesn't move for some reason. It only moves. Okay, so you see that wedge comes out. Great. Okay, so let's look at some example, the one that I typically use in the class. For this one, we basically look at the safety factor, right? We don't use any other options. Probably there is something like support and other stuff, statistics. Usually we just go with analysis and go to project settings. And the project settings it has units. I usually don't change anything. And type of analysis, deterministic, probably the easiest one when we don't have a range of values. We just have one value for each parameter. So that's what we're going to do. I'm going to click OK. And the next one, we're going to analysis. We're going to input data. And here what we need to use slope, tab, and joints. If we want to see the effect of water, we can go to water as well. I will show you later what we can do. But first, let's start with a slope. For slope, I will need to know deep direction of the slope so that it will help us to shape this wedge. So what we know. The example that I use in the class, and this is what we actually got from site investigation that we performed 3 years ago, that slope face has a deep 60 degrees. So 60 degrees means inclination or angle of the slope. And deep direction, it's direction towards north. It's 37. So I'm going to write 37, deep direction of the slope. So height of the slope, that wasn't very high. It was 8 meters, the one that we measured. And also it had upper face. So upper face, it's like this top part of the slope, if you can see it, what I show with the mouse. So upper face, it's kind of like very top part of the slope. Usually it's kind of gentle, right? So in this case, we measured it was about 10 degrees. So, and deep direction is the same as direction of the slope because it's on like part of the same slope. So the unit weight, we use the same as it's given here, so it's 2.6 sorry, density was 2.6 tons per cubic meters. So it will give you unit weight. It's about 0.026, like very close to this value. I'm not going to change this one. Even if you change to 0.025, if this is what you get from your calculations, you're not going to see any major effect on the stability of this load, because it's very, very minor change. Okay, so but what can really affect the stability of this wedge? It's deep in deep directions of these two joints, and also these numbers, which is the cohesion and friction angle. Um, Typically, when we have this wedge failure, and you will see that this actually already happened, usually for this case, the cohesion is 0. So, and this weight just slides because of the gravity. So it's basically shear stress against this friction between the wedge and these joints. Okay, so for both joints, when we measured, our estimation was that friction angle was 35 degrees, so it's already preset at 35. I think it's pretty common. And cohesion was 0. If you, for example, get like different values during your site investigation, you can change, right? So, then we look at deep direction of both joints. So for the first joint, deep direction, which is inclination of that plane was 40 degrees, while the deep direction was 60 or 060. So we put it here. For the second plane was 70, but deep direction was 320. Waviness in degrees, we kind of like simplified our analysis, and we assume that there is no waviness. So it's kind of a like straight plane, straight joint. Okay, so now I'm gonna click here, OK, click, and you see that the safety factor is 1.11, right? I'm not sure why there is like four decimal digits. So I don't think that makes sense, because when we do slope stability analysis, we'll need to round the safety factor. There is no way we can estimate it with such precision accuracy. So when I see that the students show reports and say the safety factor is 1.1132, they typically lose marks, because you don't just copy and paste from the software. You should be able to analyze it. There is no way we can get such accurate a number with the kind of assumptions and measurements that we do in the field. Okay, so what I want to show now, it's the effect of water. You see that safety factor is 1.11. So this means that, well, the wage probably should be still somewhere here. I'm going to put it back. Oops. Doesn't move, right? So let's see if we try to add a little bit of water. So we're going again to input data, and I'm going to go to water, and let's say we have rainfall. I'm going to click here, joint water pressure, and this one is percent filled. Let's say that there was some water, a little bit of damp, so I'm going to put 20% here. So percent field of the joint. Now I'm going to click OK. So you see that safety factor decreases a little bit, right? Not very much. Let's say that there is a heavy rainfall, and there is more saturation along these joints. Let's say I'm going to put here 50%, right? Um, then it goes down a little bit. Um, let's see what happens if I put 100% here. 100%. 100%, you see it drops like too much. So I believe that when there is a very high effect of water, it will decrease the friction between the wedge. It will decrease it and the joints, and then it will be much easier for this wedge to slide. You probably know by now that if safety factor is less than 1, we consider the slope unstable. Well, I'm not sure if it's true in real life, but in our slope stability analysis, that's what we do. Okay, that's it for this software. Thanks for watching and have a nice day. Bye.